Welcome back. So today we're going to build up the Hamiltonian that corresponds to being somewhere, right? Or having some we're going to build up the Hamiltonian for wave functions. And I want to do this again by going back to what we understand about the idea of having an operator and taking a measurement. So last time we developed some intuition for what it meant to have eigenstates of the position operator, right? Each point along the line is an eigenstate of the position operator. And to have eigenstates of the momentum operator. That is to say, we had a way of saying, this thing has a certain amount of momentum. And we were able to say that my particle, right, or my state, could be decomposed then onto the eigenstates of the position operator, and by decomposing it onto the eigenstates of the position operator, I generated that thing that we call the wave function, which is the thing that tells me sort of the probability amplitudes for where I expect the particle to be, right? And that's how we came up with the idea for a wave function. So today I want to start there by now thinking about how we could calculate that wave function. Now, I say calculate in kind of a funny way because we're never actually going to do this, right? But it's the procedure of finding out where, it's the procedure for extracting that wave function as part of the state. So I go back to my definition where my state is decomposed onto the eigenstates of the position operator, and the decomposition coefficients, right, or whatever you want to call them, the probability amplitudes, the pieces of information that tell me how much of that state is in each place is given by the wave function, which we're calling psi of x. Now, if I want to solve for those psi of x's, well, you kind of know how to do that, right? If I want to get out probability amplitudes, if I want to extract expansion coefficients, I have to use the Fourier trick, right? So what I'm going to do is I'm going to take another state, right? And for the moment, I'm going to call it x prime, although I'm going to switch the x's. Let me just switch the x's. I'm going to take another state, x, and I'm going to dot it into the state. I'm going to take another eigenstate, x. I'm going to dot it into my wave function, and then I've changed the x under the integral to be x prime because that's just a dummy variable, and I can push my my bra x into the integral, and I get this inner product of bra x psi times x prime, right? Now psi are just numbers, and so that the x and the x prime line up right next to each other, and I know that those two things are always going to be zero except for x equals x prime. It's just the Dirac delta, and so I can replace that entire thing with the wave function times the Dirac delta. Okay. And this is a standard sort of procedure, right? It's exactly what we used to do with the Fourier trick for finite and discrete vector spaces, right? But here I get the Kronecker delta, I get the Dirac delta instead of the Kronecker delta, which allows me to do that integral, to get rid of the integral, and enforce this to not be zero only when x is equal to x prime. And that is the procedure, right? That's the way to think about getting the expansion coefficients, the way of thinking about getting the wave function out of the state, right? Is that I take the state and I project it onto the eigenstates of the position operator, which now that I say it that way feels so great, right? I mean, I'm literally saying I take my physical state, my electron, my proton, my hydrogen, whatever it is, and I say, if I project it onto the eigenstates of the position operator, I'm really saying, give me some idea of where it could be, right? What are the potential outcomes for this particular state? But that begs the question then, if my eigenfunctions have, or if my states have wave functions, could I use this projection to get the wave function for one of the eigenstates of the position operator? And I'm going to slow down how I talk about this for a minute because there are a couple of x's here, and this is going to start to sound a little bit more subtle, and I don't want to get confused in the notation. So here I'm choosing some specific point along the x, along the number line, right? I'm going to call it x star. And that is one of the eigenstates of the position operator. And we ask ourselves, well, what is the wave function of that eigenstate going to be? For the discrete case, right, this was simply a question of if I had an operator in its own basis, right, there would just be a 0, 0, 1, 0, 0, right, there would be a 1 somewhere, and that would be the vector, that would be the ket that corresponded to that eigenstate. Here, I want to find out what's that function, right? What's the wave function that helps me to define that particular eigenstate? And of course, all that means practically is for me to take the x bra, right, and dot it into the x star ket. And that thing is, well, look, it's just the Dirac delta, right? That was our definition of the orthogonality of these states. And so what's cool is that I can use that definition now to say that this Dirac delta function is the eigenfunction, right, is the wave function for one of the eigenstates of the position operator for the eigenstate located at x prime. But now you say, Tom, delta functions, those are cool, right? I remember those. I remember when you used to talk about those back in oscillations and waves. But you also now, you have the eigenfunction, you have the eigenfunction, the wave function for the position space, and you have the wave function for the momentum states, or the eigenstates, the momentum operator, and the relationship between the eigenstates of the position operator being delta functions and the eigenstates of the momentum operator being e to the I px's, right? These are the two wave functions. So those things are things you know, right? I mean, what's the relationship between a delta function and e to the I px? It's the Fourier Transform, right? And so now the Fourier Transform seems to be some way of translating between the wave function as decomposed into the position states and the wave function as decomposed onto the momentum states, right? That I see that there's this cool relationship between writing down the wave function in terms of position and the wave function in terms of momentum. We can actually we can clarify this and solidify it a little bit, but there is one note on that previous slide that I really need to take care of, and that's that normalization factor, right? So now we're adult enough to say the eigenstates of the momentum operator, which we were calling psi sub p before, we're just going to call those p, right? Those are good eigenstates of the momentum operator. If it's a good wave function, it has to be normalized, and so I'm going to say 1 has to equal p dot p, right? That's the normalizing a wave function. So I plug in 2 copies of p. The bra version has an x prime. The ket version has a regular x. I go through this and I find that, there's a delta function of x prime minus x here. That allows me to do one of the integrals. It also sets x prime equal to x, and so e to the minus something times e to the something, that gives me just 1, and so this is infinity. That's no good, right? So there's something very weird already about the wave functions associated with the momentum state operators. Sorry, let me say that very clearly. There's something a little bit fishy about the position space wave function of the eigenstates of the momentum operator, and that it doesn't seem possible for me to find some amplitude for which this thing is normalized, right? And so I do the best that I can, and I just, let me just write it down here, and I just say I'm going to normalize it by hand and say it's 1 over the square root of 2 pi h bar times e to the I over h bar px. I'm going to give it that normalization. Okay? This is what's called the Dirac normalization, and it's something that's going to be awfully convenient for us. And it's something that reminds you exactly of what we did when we were talking about oscillations and waves, and we didn't know how to normalize those states there either. And so we threw this 1 over the square root of 2 pi. We have the h bar here just because of units, but basically we're talking about the same way of normalizing these wave functions. And so now you say, okay, I have the equipment, right? I have the eigenstates of P, I have the eigenstates of the momentum operator, I have the eigenstates of the position operator. I can see how translating those two things have to do with the Fourier transform. And so now we want to really just use the language of thinking about this as a change of basis. That if I have a particular state that has a wave function in terms of the position space eigenstates, that is, if I have the position space wave function, which I'm calling psi of x, I can calculate the momentum space wave function by taking the Fourier transform, right? And the Fourier transform is going to be defined the way that I have it written down here, with this overall 1 over 2 pi h bar out in front, okay? And that means that I really have two ways of talking about any particular state, at least two ways, right? I can either decompose it onto the eigenstates of the momentum of the position operator, or I can decompose it onto the eigenstates of the momentum operator, right? And the Fourier transform serves as the translation between those two things. And so when I write all of these things out, I know that projecting the state psi onto the x states is going to give me the position space eigenfunction, the position space wave function. If I project psi onto the momentum states, that gives me the momentum state wave function. And then if I want to, on the right-hand side, I have them written down explicitly as in the integral form, right? And except I have a typo here, right? This should be a p, right? Because I'm decomposing it onto the eigenstates, the momentum operator. And then the relationship between the two different sets of coefficients are just given to me by, the Fourier transform. This is pretty beautiful, right? Like, it's awesome to think about how this parallelism that we have with position and momentum now finds itself inherent in what we talk about with quantum mechanics. And of course, this goes back to the fact that if I take a position space eigenfunction, right? If I take a momentum space eigenfunction, which is the ket p, and I get the position space wave function, then I get this thing in the first line, right? So I take the eigenstate of the position operator, project it onto the eigenstates of the momentum operator, and I get out this e to the I over h bar p times x. If I flip that around, right, inner products, if I change their order, I get the complex conjugate. I also get what happens when I take the position space eigenfunctions, right? If I take a eigenstate of the position operator and I project it onto the momentum states, well, I also get an e to the minus I over h bar px, right? And so it's the symmetry is restored. The symmetry of the universe is restored, right? Because the position space wave function of the momentum states are e to the ipx's. The momentum space wave functions of the position eigenstates, they're also e to the ipx's, right? And so there's this beautiful thing about the position space and momentum space. They sort of have this symmetry associated with them that allows me to translate between the two. Okay. So what I'm trying to get across in this first half now is just the very bare notion, or the sort of fundamental idea, that I take my state and I can decompose it onto the eigenstates of the momentum operator, or I can decompose it onto the eigenstates of the position operator. And that doesn't harm the state. It's just a different way of writing it. It's putting it in a different basis. And that the Fourier transform gives me the translation tool to go between those two bases. Okay? And if I'm writing it down in terms of the position state eigenstates, I call it the position wave function. If I'm writing it down in terms of the eigenstates, the momentum operator, then I would call it the momentum space wave function. So now I'm ready to talk about, well, what happens if neither of those prescriptions turn out to be the right one? That is, what happens if I'm trying to define a state But I want to measure its total energy. So I know that the total energy, which we're going to call the Hamiltonian, right? There are certain caveats to that, but the total energy is given by the Hamiltonian operator, which is going to be made of the kinetic energy and the potential energy. Now, you know that the potential energy 1/2 mv squared can also be written in terms of the momentum, right? P squared over 2m. That's just a way of thinking about the kinetic energy is really inherently a property of the momentum of a particle. But the potential energy only depends on x, right? Now, this is something special, right? We knew that the potential energy comes from the potential energy comes from conservative forces. Conservative forces can only depend on position. They can't depend on other things. Otherwise, they're not conservative forces, and I can't talk about a potential energy associated with them. And so I have two terms of my Hamiltonian now, one of which clearly corresponds to the position space operator, right? The position operator, x. The potential only cares about x. And I have the kinetic energy, which only cares about p, right? And these two things are not the same, right? One of them is asking about the momentum of the particle. The other one is asking where it is. And when I look back at these, if I look back at my previous couple of slides, I start to get worried because we showed that, like, if we know where a particle is, if it's in an eigenstate of the position operator, then its momentum is totally spread out, right? It's e to the I px. It's even unnormalizable, right? It's everywhere. Oh, sorry, it's not everywhere. It has every possible value of the momentum. And so our brains are starting to think about commutations, and it's starting to think about which basis is good, and it's starting to panic a little bit. We don't have to worry too much now, right? Because what we realize is that tension between the position space and the momentum space and the position operator and the momentum operator are exactly the tensions that are going to say, maybe this can be solved if the Hamiltonian has only certain solutions. That is, if there are only certain functions for which the Hamiltonian has eigenstates or has eigenvalues. That is, can the Hamiltonian give us a discrete Hilbert space out of my all possible types of wave functions? But in order to do this problem, I have to make a choice. And the choice that your book makes, which is the choice that every book makes, which is the choice that we're going to make, is to start by thinking about these problems explicitly in the position space representation, right? So I'm going to put aside the fact that I get so nervous when I try to represent momentum in position space. I'm going to work in position space basically because I don't know what the potential is going to look like. Although I do know that it's going to be a position space thing. I also know what the momentum operator looks like in the position basis, right? We wrote that down last time. The momentum operator in the position basis is minus I h bar d by dx. And so I can plug that in, right, to p squared, and I get that the Hamiltonian is minus h bar squared over 2m d by dx squared plus the potential, right? Where the potential has a certain number or a certain function of the position operator that's inside of it. We don't know what it looks like yet, but we're not going to worry about that until we have a concrete example. So now that we have this, our goal is to say, well, if I have a particular Hamiltonian, if I have a particular potential, can I use the position space wave function to find out whether or not there are discrete states of the energy? That is, can the Hamiltonian satisfy an eigenvalue equation, which of course means taking my Hamiltonian in position space and plugging it in, and then decomposing the state onto the eigenstates of the position operator so that I get the wave functions out, etc. I can then explicitly set the left-hand side of this equal to the right-hand side, right? In order for those integrals to be equal to each other, Okay, not in order, but all the time. Physicists, blah, blah, blah. If the integrals are equal to each other, it's easiest for the integrands to be equal to each other, and therefore I can, if I solve the integrands being equal, I will automatically get the integrals being equal. And so I'm left with this expression, which is an eigenvalue problem, right? It's an eigen, because I'm looking for an operator acting on a wave function equals a constant times a wave function. And I have this beautiful equation where I'm trying to find out, are there solutions to this that give me constants e sub I and wave functions psi sub I that satisfy this differential equation. And for many of us, we suddenly feel good, right? Because for the last 6 weeks, we've been talking about kets and bras and e's and all this, in spookiness. And now we somehow get back to, a differential equation that might have boundary conditions or might be able to be solved using calculus. And I don't have to worry about things because I'm just going to solve for functions and constants. And I'm used to doing that in physics, and so things aren't going to be so bad. And maybe it's not going to be so bad. But at the heart of this is still a quantum idea that we're searching for eigenstates of the Hamiltonian by using wave functions, which are, of course, the probability amplitudes of eigenstates of the position operator. Okay? But the wave functions I'm solving for explicitly in this form are the position space wave functions. And then if they satisfy this, I will be able to generate eigenstates of the Hamiltonian, and that reduces my Hilbert space to one that is discrete. Possibly discrete. Could possibly. Okay, so all of my take-home messages. There's this great inner product between the eigenstates of position and the eigenstates of momentum that are given by this e to the I px. And that allows me to restore the symmetry between position space and momentum space. I have two different kinds of wave functions. The one that we're most going to deal with, at least for the next week or two, is the position space wave function, which is decomposing my state onto eigenstates of the position operator. But I also have a momentum space wave function, which we discovered today is just the Fourier transform of the position space one. And if I work in the position space, I can write down a Hamiltonian for the particle, which is an eigenvalue equation, and then I can try to solve that equation to find out whether or not the Hamiltonian has states that obey this particular eigenvalue equation. Okay? Next time we'll have to do some real concrete examples.